So because these eigenvalue equations are so important, remember that if a wave function is an eigenfunction of an operator, then when I measure that observable, when I make a measurement for O, for the system that's described by that eigenfunction, I always get the value of O with no variation. So there is, in fact, only instrumental uncertainty and no inherent innate uncertainty in the value of that observable when my system is described by a function which is an eigenfunction of the operator that returns that observable. And so let's see how this works. Let's do a couple of examples because this is such an important concept. So let's just imagine that our eigenfunction looks like this. It's a plane wave. So it's equal to I e to the I p sub x times x over h bar. So we'll let k equal kx equal p sub x over h bar, just to simplify this out a little bit. So let's let our wave function equal some constant e to the I kx times x. Now let's see what happens when we operate our momentum operator on psi. So the momentum operator is minus I h bar. Take the first derivative with respect to x of psi. So the first derivative of this function, so I have my minus I h bar. A is just the constant, so that just comes out. The first derivative of an exponential is the exponential, but I have a function of x up here, so I have to use the chain rule. So I take the derivative of the whole thing times the derivative of what's inside. And the derivative of what's up here is I times kx. So I'm going to get an I kx out, and then I'm going to get my exponential back. So if I simplify this out a little bit, I've got p hat psi is equal to, okay, now we got to do some imaginary stuff here. I times I, remember that I is the square root of minus 1. So if I square I get square root of minus 1 squared, or minus 1. So I squared is minus 1. So I times I is minus 1 times this minus is a positive. So I have positive h bar kx, and then a e to the I kx times x. But this is just my wave function. So p hat in the x direction psi is equal to h bar kx psi back again, which means that because I have a constant times my wave function, that when I operate the momentum operator on this wave function, I get a constant times the wave function, and this constant is my eigenvalue. And so psi being equal to e to the I kx is an eigenfunction of the operator p hat, and it has an eigenvalue of h bar k. So that means that I can know the momentum of this particular wave function exactly with no uncertainty. Now, what happens when I operate the position operator on that same wave function? So remember that the position operator just says multiply the wave function by x, right? So I have x times a e to the I k sub x times x. And now I have a variable. This is not constant with x. It's variable. It changes when x changes. And then I have my wave function back again. So psi is not an eigenfunction of the position operator, which means I have no idea what the position is. So to make sense out of this, let's just take a look at what this wave function looks like. So if I draw this wave function, it's really just sines and cosines. So as a stationary state, it looks something like this, right? And remember that for a wave, that the wavelength is related to the momentum. So again, I've got this in units of h bar. So let's just divide both sides by 2 pi so that we have lambda over 2 pi is equal to h bar over p, okay? And so if I want to know what the momentum is equal to 2 pi over lambda times h bar. So 2 pi over lambda is my k value, because we said that p was equal to k times h bar, or h bar times k. And so this k that I defined tells me about the wavelength of my matter wave, of my wave function. And I know that exactly because this plane wave, this e to the ikx times x, just looks like this function here, and it has a known wavelength. I know exactly what that wavelength is because I know exactly what my k value is. However, if I try to decide where that wave is, it can be anywhere. It's all everywhere on the x-axis. And so I have no idea actually where it is because it's everywhere. And so it makes sense that x is not an eigenfunction, or that psi is not an eigenfunction of the position operator, but it is an eigenfunction of the momentum operator, because this wave has a set wavelength, a set k value, and it exists everywhere on the x-axis. So because this k value is related to the wavelength of the wave, we often call this the wave vector. So k defines the wave vector for my wave. So if I can't know where my particle is exactly, I might be able to calculate an average. And in quantum mechanics, we call these averages expectation values. So what I want is an average value for x. So if you think about how, when we have a continuous distribution, how we calculate average values, we take and we integrate over all space for each possible value of my observable position, x in this case, times the probability that that particular value of x is going to be measured, and then I integrate over all space. So let's think about what we have here. So x is given by x operating on psi. That should tell me something about the position. And psi star times psi dx tells me about the probability. So if I put these two things together, psi star x hat psi integrated over all space should tell me about the average. And this is how we find an expectation value quantum mechanically. So formally, a average value, or an expectation value of an observable, is equal to integrating over all space the wave function, complex conjugate, times the operator for that observable operating on the wave function integrated over all space. But I need to make sure that my probabilities are good probabilities, and I need to make sure that they all add up to 1. And so I need to include a division by psi star psi d tau so that I normalize my probabilities so that my probabilities all add up to 1. So this is the formal definition of the expectation value of an observable. Notice that this numerator here is related to our definition for a Hermitian operator. And so we said that for a Hermitian operator, that this value, the integral overall space of psi star times the observable times psi, will always be a real number. And that's important because we want our average values to be real numbers. And so if this was not Hermitian, this might not be a real number, and then it wouldn't make any physical sense. And that's why our operators have to be Hermitian. So to see how this works, let's find the average value of x for our plane wave, where psi is equal to a e to the I kx times x. So what this tells me to do, because x can be anywhere from minus infinity to infinity, is to take a e to the I kx, but I have to make the I negative in order to get the complex conjugate. So that's the complex conjugate of psi. And then I need to operate on the wave function itself and then integrate over all x's. Divide that by my normalization condition, psi star times psi integrated over all x's. All right, so my a's are just constants. So I can pull that out of the integral. There's a times a will give me an a squared out here. And then minus infinity to infinity. And notice that e to the minus ikx times e to the ikx is just equal to 1. And so I'm left with x dx here. And then I'm dividing by a squared again, because again, I have a times a, which pulls out of my integral to be a squared. And then e to the minus ikx times e to the ikx is just equal to 1. And so I have dx, and I'm integrating from minus infinity to infinity. And so what I end up with is a little strange here. So I have a squared 1/2 x squared from minus infinity to infinity divided by a squared times x evaluated from minus infinity to infinity. And so I have, what do we have here? So my a squareds are going to cancel out. I have 1/2 infinity, so I have infinity, minus a infinity, minus infinity squared. Minus infinity squared is just infinity, so minus infinity. And then when I evaluate the denominator, I have infinity minus a minus infinity. So I have the average value of x is infinity minus infinity divided by 2 infinity, and that is just equal to 0. So anything minus itself, including infinity, is 0, so 0 in the numerator. And then my denominator goes to infinity, and the bigger the denominator gets, the closer that value gets to 0. So this is truly equal to 0. So my average value of x is at 0.